Cool. All right, well, let's get started. First of all, I wanted to thank the organizers of Code Blue for having me, and thanks everyone for coming. Great keynote, Jeff. It was a very good way to start it off. But I'm going to be talking about automotive security, specifically within the internals of the computers used in modern vehicles. A while back, Dr. Charlie Miller and myself started doing some research into automotive security. I think most people here probably know Charlie. He was the guy who first hacked the iPhone and all that other stuff. I traditionally was doing Windows exploitation work. I reversed a lot of the Windows heaps, like Windows XP through 8. So I did exploitation work, and I wanted to do something different that wasn't just software, something that was maybe even more impactful than owning a PC. So we both decided, why not try to hack cars? Today, we're going to talk about a few things. I want to go over the anatomy of breaching an automobile. I think sometimes people are confused on exactly what that is. We'll look into some CAN basics. That's the controller area network. Cars these days use CAN to communicate with each other. We'll then, after learning about CAN, show you with a bunch of videos of how we attack the CAN network to control physical attributes of the automobile, such as braking, steering, acceleration, lights, things like that. And instead of doing the normal offensive security researcher thing and just ending with all the things that we broke, Charlie and I really decided to come up with some elegant solutions on solving problems with automobiles, specifically detecting and preventing attacks. When most people think of attacking an automobile, they think of it remotely, right? Whether it's from a movie or a James Bond, or generally speaking, you want to compromise the car remotely. And there are a lot of entry points in an automobile. The one most people are probably familiar with is Bluetooth. Almost everyone's car has Bluetooth in it, so you can talk over your wireless headset, play music, etc. This also, from an attacker's perspective, is an entry point, right? It's an attack vector for someone like me. Telematics units are also very popular. GM has OnStar, Mercedes has Embrace, and I think Toyota has some SOS type system, right? These are the things you hit the button and someone can help you. Or if your car is stolen, they can shut the automobile down. There's a lot of connectivity. Cars are even included with Wi-Fi now, right? They want to interface with your apps, your phone, all this other stuff. More and more things are added to cars. From an attacker's perspective, those are more and more entry points into the automobile. There's also intermediaries as well. There's these neat little dongles that people are using to track driving habits. A lot of insurance companies use them. I have this little thing called a Fleet Karma. They mainly are designed to read from the CAN bus over ODB2. That's your diagnostic port in your car. They don't come with the functionality to write. The nice thing is some of them are open source, and I'm currently writing a custom firmware for my Fleet Karma device so it can read and write to the CAN bus. So that means all the attacks I'm about to show you that we did locally plugged in could be done somewhat remotely if you got this device plugged in and was around the car or had 3G capabilities. So that's how you generally go about getting remote access to a car. But once you have remote access, whether you exploited a vulnerability or plugged in your dongle, what can you do? You want to inject CAN messages. There's a lot of the automobile that relies on reading messages from the CAN bus to do certain things. Am I about to be in an accident? If so, apply the brakes. That's a very natural thing for a car to do. We'll talk later on some deficiencies with CAN as an architecture, and not blaming anyone, but we'll show you why these deficiencies make it easy for attackers to figure out how to manipulate the car. So your ideal attack scenario would revolve around having a remote vulnerability that could be exploited. Let's say there is a stack overflow in the Bluetooth stack pre-authentication. You could compromise the car's infotainment system, but then what? So you're running code on a device on the car, but the infotainment system in itself doesn't do anything. I mean, it plays music, it gives you directions, but it doesn't physically control the car. You need to learn the local parts, the stuff that Charlie and I did. Each car and each manufacturer is proprietary in the way they send messages. The Ford that I'll show you was way different than the Toyota with the way they sent messages and how they were used. So you need to understand these to physically control the car. The learning of the proprietary messages can actually take quite a bit longer than figuring out a remote exploit for a vulnerability in some kind of wireless entry point, because the wireless entry point can be somewhat universal. It may affect a whole fleet, right? It may affect a whole brand, but each car in that brand most likely is going to be a bit different. So you're going to have to figure it out for each automobile. That's good from a security perspective because it makes an attacker's job much more hard. So what do you actually go after? And what we looked at were ECUs, or electronic control units. These really gained popularity, I think, in the late 70s or 80s, mainly revolving around gas consumption and efficiency, right? Nowadays, these ECUs control almost every aspect of your automobile. The gist of it is they take input from sensors and they provide output to things like actuators. For example, it senses that one of your tires is skidding, right, when you press the brakes, and therefore it will apply the anti-lock braking system. Sensor provides input, the computer makes a decision, and provides output to the actuator. You have to remember, though, that most of these computers, excluding your infotainment system, are custom code running real-time operating systems. These aren't just little Linux boxes. These are very small CPUs with a very specific job. For example, in the Toyota Prius, there was an ECU whose sole job was to sit on the CAN bus and listen for a message with a specific value. And when it saw a message with a specific value, it would tighten your safety belt. That was involved in the pre-collision system. It tightened your safety belt so your face didn't smash into the windshield. Very cool, but you have to realize there's all these little computers throughout the car that have very specific jobs. They're not your general purpose laptop running a word processor and a web browser and chat clients. They're designed for a specific purpose. They have really, I guess you could call almost a token ring structure. So the CAN bus is set up so every node that's on a bus can communicate with every other node. They're always periodically broadcasting information, right? For example, a computer that broadcasts the speed will always be broadcasting the speed perpetually, so many times a second, right? It's not like they happen ad hoc. They're just always happening. And the only way the other ECUs know what to do with it is they have an ID and a value, which we'll talk about. And it'll just say, hey, I'm interested in that. I'll consume it. Or here's the IDs I spit out. It's really quite elegant and quite simple. If you're looking for these ECUs in the car, when we started this project we were not mechanically inclined at all. I don't change my own oil in my car. I take it somewhere. So we really were ripping these cars apart. This is a connector for the Ford PCM module, which is used for the engine. We found that if you find a bunch of pretty colored wires going somewhere, most likely going to be a computer in your car, not so shockingly. Once you take these out of your car and take the lid off, they look very much like some kind of embedded device, right? You see a PCB, there's some stuff and things. It's nice to know, too, when you take these out, we started looking at them for markings and everything as well, because as exploit writers, we realized if we wanted to, say, write shell code for these, we would need to understand what their architecture was, what kind of CPUs they had, how much memory they had, things like that. So those are, the ECUs in cars, and that's generally what they look like. If you're not familiar with the controller area network, don't be alarmed. It's really simple. Honestly, the Wikipedia page does a great job of explaining what it does. But our short version is each message has an ID. The ID is either 11 bits in length or 29 bits in length. You usually don't see mixed 11-bit and 29-bit. For passenger vehicles, 11-bit seems to be the standard. If you get into heavy machinery like big rigs, farming equipment, they tend to use 29-bit IDs. Each ID contains a payload when it's sent on the bus. It can either be 0 to 8 bytes in length, right? And it's really simple. You can just look at these bytes, and it either has 0 or 8. There's a little bit of a caveat to that, but I'll talk about it later. What you should know is the ID is used as a priority field. So, for example, ID 0 is the most important message, right? They set it up this way so it's easy to arbitrate conflicts. And also, it's an easy denial of service from an attacker's perspective as well, right? You keep sending ID 0 with a payload of 1 byte of 0, and that's the most important message on the bus at that time because you gave it that ID. It's broadcast in nature. As I said before, you saw how the ECUs were chained up. There's no addressing. You are not sending messages directly to a braking ECU. You're just putting a message on the wire with an ID that the braking ECU is aware of. It doesn't ask where it came from or who put it there. It just knows that it's there for it. And we were mainly interested in the application data, the bytes. There's some other stuff that you could be worried about, but we just wanted application data. There's normal CAN messages, as I talked about before, that are constantly being spit out onto the bus, right? Here's the current speed, here's the current speed, here's the current speed, here's the current steering angle, here's the current steering angle. They're always happening. Here's a format that I invented on a plane because I didn't have the internet and I didn't have the man page for string tokenizing, but I did know how to write a state machine that parsed spaces and commas, and that's why this is a super simple way to show this stuff. We wanted it to be human readable and also digestible by our API. So all the tools and all the data and everything for all this work that we did, we published. We want researchers testing our work and expounding upon what we did. We figure with more security people in mind, doing automotive research, we can make cars more secure. I said before that ECUs are constantly spitting out information, right? That is the case. At the same time, there are diagnostic messages as well, and they're pretty descript. These are what mechanics use to send a certain message to a certain ECU. It's not really a addressing, but what it does is it will send a message out, and the reply is 8 more with the ID. So if you see here, the ID is 0760. The ECU replies with ID 0768. This is just a way for mechanics to diagnose certain computers in the car. For example, they might say, hey, engine ECU, can you tell me the status of your oxygen sensors for emissions testing? And it will give it data back. You normally don't see these when you're driving the car. The reason they're diagnostic messages is they're used for doing diagnostics when the car is, say, up on jacks, right? Again, while they are mainly used by mechanics for mechanical work, we'll show you how we leverage them to be used while we were driving the car as well. As I said before, there's some standards and protocols that I don't like to go into because they're boring, but if you would want to read about them, here are the ones that you should use. One is called ISO-TP. That's a way of sending more than 8 bytes on the CAN line. It actually sends chunks of 8-byte values. And then there's ISO 14229 and 14230. These describe, if you plan to implement them, services on the ECU. Think of it much like a service that runs on a box on the internet, whether it's SSH or HTTP, something like that, but for automotive purposes. For example, ECUs tend to implement the security access service. And the security access service is a way for a mechanic to get privileged access to an ECU. Say it wants to reflash the firmware. They don't want that to happen when everything's going on. You put the ECU into privileged mode, and then you can perform your work. And there's a challenge response sequence, but as you see here, there's no key exchange. We'll talk about why there isn't any and why it's trivial to defeat this security access here in a little bit. There's also other really neat services as well that some ECUs implement. For example, input and output control. You can think of this almost like RPC for things in the car. Mechanics really like to test things physically without physically touching them. So you can say, clamp the right brake caliper. They want to do that because they want to test to see if it works before taking the wheel off and doing a bunch of manual labor. It saves them time, and it saves you time and money. So there's a bunch of neat things. Here's some other services that can be implemented but don't have to be. Originally, when we started doing this research, we got super excited because we saw services that were defined as request download and request upload, right? That's give me your code off the ECU, here's code to put on the ECU. We figured car hacking would take us all of 3 weeks, we'd be done, and we'd be internet famous. Needless to say, while we did gain a bit of internet infamy, these services aren't always included and almost never are included. For that reason, you wouldn't want your competitor to immediately be able to get your code and then write new code on there, right? So while these services do exist, it doesn't appear to be that most manufacturers implement them. So we got our overview of CAN, how it worked, how messages worked, how diagnostics work. These things implement services. There tend to be some very systemic issues with this. One of them is that CAN was designed decades ago by Bosch. They didn't know that cars would ever have connectivity to them. Do you think Bosch in '79 thought a car would have a Wi-Fi hotspot or OnStar to turn off the engine? No, so they designed a simple system that would work under the circumstances. CAN, by design, doesn't support any authorization, authentication, or encryption. So that means that the ECUs on the bus implicitly trust every other ECU on the bus. If it sees a message that is known to be about braking and it listens to those, it doesn't ask where it came from. It assumes it came from the braking ECU. That's not necessarily the case, as we'll show you. And right now, the entire automotive industry seems really focused on solely controlling the entry point from a security perspective. And to me, that's like saying, I have a firewall, don't worry, everything behind it is secure, because nothing will ever get through. As someone who writes exploits and did penetration testing for a living, I would like to think that having a bit of more tiered approach would be more reasonable than just saying you can't hack our Bluetooth stack or you can't hack our telematics unit. For people like me, that's a challenge. I want to do it now, right? These attacks will vary over time, but I think we'll show you that the anatomy of actually controlling a car once you've compromised it tends to be pretty standard. Current attacks that we'll talk about really rely on CAN injection. But there's some limitations. The first being, right now, not all functionality for an automobile relies solely on CAN. For example, in the Ford Escape, although it was accelerate by wire, there were sensors on the acceleration pedal, and when you pressed them, they would send information to the engine control module. But it never went over the CAN bus. So while it was controlled by a computer, it wasn't sent over CAN. Not everything is done by CAN in cars. This may, it's going to the point where more and more things will be on the CAN bus, but right now everything isn't. You have to realize too, when you're forging these messages, you're competing with the actual ECU that's sending the legitimate data. For example, the accelerator data, the actual pedal and sensors are sending the correct messages on the CAN bus. We were sending forged messages saying the pedal was down the whole way. How did we get ours to work? We just shouted louder and sent it faster. If they were sending it 10 times a millisecond, we sent it 10,000 times a millisecond. So you kind of really have to outshout them, and it doesn't give you perfect behavior. I'll show you specifically with steering how it ended up not being very fluid. Safety features need to be bypassed as well. There are safety features in these cars when reading information from the CAN bus. Again, a lot of it, though, is usually read from the same trusted place, which is the CAN bus, so we can kind of circumvent it. So now it's time to show you all our parlor tricks here in our movies. I'm going to skip over the Ford speedometer one that Charlie did because he messed up his video. Shame on you, Charlie. But I will show you how we changed the, oh man, do I have audio? There we go. I will show you how I changed the speed on the combination meter of a 2010 Toyota Prius by sending messages on the CAN bus. And if you could listen, you'll hear it start beeping, and you'll see it tell me to put my seatbelt on, and I'll explain that to you. Okay, we're obviously in park. We're not going anywhere. And we're going to set the speedometer to say we're going 20 miles per hour. And it thinks we're moving. So, there's something to notice. While changing the speedometer reading is a bit of a parlor trick, obviously we could set it to whatever we wanted, you heard the beep and it told you to put your seatbelt on. And that tells you something. That tells you how the CAN bus works. There's collateral damage for sending messages out like that. Not only were we tricking the speedometer into thinking it was going 20 miles an hour, but every other ECU on that car that is dependent on listening to speed also saw that the car was going 20 miles an hour. That's why it said, hey, put your seatbelt on. You must be going 20 miles an hour. So while you may send a message that will affect one thing, it could actually affect many things since they're all on the same broadcast bus. Braking in the Toyota was achieved by looking at the pre-collision system right before you were about to be in an accident and then mimicking that traffic. You might ask, Chris, how did you figure out how to almost be in a collision to get this to work? So what I did is outside of my house, I stacked 4 huge garbage cans, and I would back the car up, and then I would hook up my sniffer, and then I would drive the car full speed and wreck through the garbage cans. And I did that several times a day for about a week, and I finally figured out the messages that I needed. My neighbors think I'm a crazy person now, but we did figure it out. So we're braking there by telling the car, hey, you're about to be in an accident, you should press the brakes. And it clamps the brakes. And you can actually give it a percentage that you want to clamp. Sometimes it'll slow you down. Of course, we put it to 100%. As long as we played that message, the car could not move. Because the engine wasn't powerful enough to move the wheels once all the calipers were shut. So again, it's neat to know that you could completely immobilize the car just with its own brakes. Additionally, this I thought was cool because we used the car's own safety features against it. The pre-collision system is amazing. It's actually prevented me from wrecking the Prius into another car because if you're not paying attention, it will brake for you. But at the same time, from an attacker's perspective, they can use this type of technology to completely lock the brakes and never let them go. Here's, I think, one of our main contributions, at least to this research. When we bought these cars, we wanted to ensure that they had parking assist features. You know, the car that'll parallel park itself. We figured if a computer turned the wheel of the car, so could we. And lo and behold, we were correct.
Right now, I think it should just spin the whole way around, too.
You'll see the wheel turns be quite jerky. I tried to kill Charlie many times. And here's a view.
We almost died, man.
We were in an abandoned lot, and in those weeds was an old steel I-beam, and we almost hit that, so we were terrified. But the reason the wheel didn't turn fluidly is because there were some safety mechanisms on the Toyota Prius. The Toyota Prius would not let you would not let the wheel of the car turn unless the car was going less than 5 miles an hour, it was already in the auto parking mode, and the car had to be in reverse. So how did we get it to turn the wheel violently when we were actually driving 25 miles an hour? Where do you think they read if the car was in reverse, the speed, and the parking mode? They read it off the CAN bus. So we just kept on pumping messages onto the CAN bus saying, hey, we're parallel parking itself. Hey, we're in reverse. And then we would flood it with a speed that it didn't know. And you would see the wheel turn after a beep. So what would happen is we would flood the network with a speed it didn't know. Some computer would go offline. The moment that computer went offline, we would send our message to turn the wheel, and pandemonium ensues. Right? So there are safety mechanisms, but at the same time, you can also trick them. Acceleration is another thing that we could do in the Prius, since it was really accelerate by wire. While it was on a segregated CAN bus, we wanted to show that you didn't need to just plug into the diagnostic port. CAN is a pair of twisted wires, CAN high and CAN low. So we just found where that bus was and clipped right in, and we could accelerate the car. And you'll kind of see me try to lift my feet up, and you'll hear the car continue to accelerate. Even when I stop the car, the engine's still redlining. Oh, and you can't turn the car off just by pressing the button either.
Can't turn the car off.
So there's a few funny stories with this. Again, to note, you don't have to go through the proper diagnostic port to do this stuff. There's actually some guys going to do a presentation where they show just clipping into the CAN bus works just as well, and it does. If we would have let that video go 3 seconds longer, you would have heard this loud pop. And the car would not start again, and we had to get it towed to a Toyota dealership. And I had to drive a rental car home back to Pittsburgh, and a few days later, a Toyota representative called me and said, "Hey, what's wrong with your car?" And I said, "Well, you tell me." He's like, "It is a complete mess." He's like, "I think we should try to put it back together." And I was like, "No, do not put it back together." Lo and behold, we actually blew up the inverter, the thing that takes, electricity and makes kinetic energy, all that stuff. And it cost us $5,000 to fix. So not only can you cause physical harm to a passenger, but I would rather wreck and break my neck than have to pay $5,000 to get a car fixed. But that's just me. So that ends that section, right? Those were all messages that naturally occur on the car. We just forged them with values that shouldn't be at that period of time and sent them. Next, we'll talk about diagnostic messages. And to do some diagnostic things, you usually have to put the ECU into a specific mode, a privilege mode, security access mode. Well, how did we figure out how to put them into security access mode? Ford had one where when we requested the seed, it was always 112233 every time. And after actually looking at the firmware, we saw that there was a branch where it should have jumped. So this is actually debug code that they forgot to take out. So it's always sending the same seed. So you always know the password for this exact one is CBBF91. That's just was kind of a mess up on their part. How'd we get all the other keys, though? The mechanics tools. This was the easiest part of this project for Charlie and I. We're reverse engineers by trade. So the mechanics tools are simple Win32 applications, and they hold all the secrets in them. Because the secrets aren't sent between the ECU and the mechanics tool. They both reside on the ECU and the mechanics tool, so you can get them from there. So there's all the keys for the Ford. Lincoln, Mercury, Mazda, to unlock ECUs in them, right? This is actually how academic researchers did most of their attacks. And they actually did theirs remotely by compromising the telematics unit and had an IRC server actually on the car.
Some kid could be messing with you just for fun.
And we'll be applying your brakes shortly. Right about now.
And you see they clamped the front brake. They used the diagnostic command after doing security access to the ECU, and they did it remotely. So I don't know, for all the people who didn't think remote car attacks were impossible, the University of Washington, the University of California, San Diego has already performed them. Well, what are some of the diagnostics that we did? We could kill the engine on the Ford, where you sent a message and the engine died. And if you kept sending that message, the car could never start up again, even if you turned it off and on.
Did you kill the engine?
That's Charlie's son.
Yeah.
And there's really nothing you can do as long as this message is playing. You can't start the car back up. Lights are also a very important thing, right? I usually keep my lights in my car in auto mode so I don't forget to turn them off and I don't have to remember to turn them on. In the Prius, if your lights were in auto mode, you could send mechanics messages without doing security access to turn the lights on and off. So again, turning someone's lights off down a dark road could be very dangerous. We did the same thing in the Ford as well. There were some other benign things that you could do, which were just neat to us. You could control the horn.
Oh my God.
and you couldn't do anything. And most people don't realize the CAN bus stays active for about 2 minutes after the car is off. So you could actually honk, if you kept sending this message, the car horn would honk for 2 to 3 minutes. Again, my neighbors had to hate me when I was testing these features. I thought this one was really neat because I always thought a horn was basically just 2 pieces of metal that when touched would activate a horn. But you realize there's more to that because they're connected now to the car's network. I talked about the pre-tensing system before. We could test that as we were driving. And you'll see Charlie get pulled back by this type of thing.
Fight it. Jesus.
And again, you can keep doing this. I actually blew out one of the motors recently doing some tests, so you can actually ruin those as well. One that people seem to like is locking and unlocking.
Lock all the doors.
You send one simple message that says unlock all the doors in the car, and it'll unlock all the doors. Again, I think for auto theft, this would be one that someone was interested in, right? Remote exploit for Bluetooth or telematics, unlock the doors, start the engine, drive away. Another parlor tricky one was fuel gauge, right? They just basically want to test that the LEDs work on the display. It started out with a quarter tank, and then I said it went to full. I really want to play a trick on my friend who has a Prius and get my little dongle and always play that he has a full tank of gas. So he runs out of gas one day and doesn't know why. After DEF CON, we got maybe one of the best questions I've ever been asked is someone came up and said, will the Prius never run out of gas? And I said, yes, I've personally solved the energy crisis. Free fuel forever. Lastly, the most terrifying for me was the capability to disable the brakes as the car was driving. While there were some prerequisites that the car needed to be going under about 8 miles an hour,
All right.
that's probably when you want to stop. You hear that growling noise. I was panicking so much that I tried to brake with my left foot, which I never do. So it was crazy. That right there, what Charlie did was get privileged access to braking, and then do what a mechanic would do, bleed the brakes before he's replacing them. Something like this should never happen while the car's driving, right? There's no need for it, but it still works. Well, maybe you're even worried about people stealing, your code. We got code off of a few of our ECUs just by identifying debug test points, buying a hardware debugger, and then dumping out the code. This wasn't over CAN, but we took them out, dumped the code out, and Charlie and I are reverse engineers by trade. This, again, was the easy part for us. We figured out where this thing was loading code, how it sent CAN messages, how it received them, and from there, we wrote code to reflash the ECU over the CAN bus and actually have our code running while the car is running, but the ECU is still performing its job. So we're calling this continued access, but if you know malware, this would be referred to as persistence. So Charlie's plugged in.
I plug into your OBD2 port for a second. I run my program.
And that's how fast it took him to reflash the ECU.
Part. And yet when you're driving along, you've got your backwards camera still on because...
So the show code we wrote just sent CAN messages telling the car it was in reverse, so the backup camera would be displayed. Obviously, we wanted to do the most benign thing in case it went wrong because we couldn't just unplug. It was running on the ECU. So not only can you perform these attacks when you're jacked in, you can also rewrite the code on these ECUs to perform actions. We could have just as easily wrote code to say, read when you're going above 80 miles an hour. When that's the case, turn the wheel 180 degrees to the left. but we didn't want to kill ourselves while we were doing this research. We saw the problems. I think we identified a lot of problems. There's problems with the architecture because some of it's archaic. There's problems because there's so much trust on the network. How do we go about making solutions for this? Right now, it seems like most of the time and effort is spent on securing remote endpoints. Everyone we talk to just says, don't worry, we make sure our Bluetooth stack is good. Don't worry, we're testing our telematics unit. People tend to say, let's cryptographically verify all these messages sent on the CAN bus, or make certain segments and crypto. We have a kind of different idea based off our experience as offensive security people. This is the kind of CAN PR statement we got from Toyota that basically said, don't worry, Toyota customers, we do testing. No one can hack into ours remotely. That being said, they apparently didn't care what we did. So I'd take that as, if you remotely breach a Toyota, you have the keys to the castle because you saw exactly all the things that we could do. As security practitioners, we don't really ever rely on a single layer. We do tiered approaches, right? And I think the same thing is needed for automobiles. Total security is not achievable. I mean, Jeff said this in his keynote. We're humans, we make mistakes. Things are always going to happen. We haven't been able to secure our networks or our PCs. I don't understand why we think cars are going to be any different. They're just a big computer, but they're 4 wheels and they go 100 miles an hour. As I said before, if an enterprise came up and told you that they have a single layered security approach and aren't interested in any tier layered security, I think you would probably get an argument with them on why they're doing things wrong. And that's how we feel about the automotive industry right now, where it's solely focused on protecting entry in. So hopefully this will get the discussion moving and we can work together to make more secure cars. ECU patching can be hard. Unless you have a Tesla, you're not usually getting over-the-air updates. So if there is some kind of fix that is needed, getting everyone to a dealership and getting their car fixed not only is hard, but is very costly. And auto manufacturers, as I've found out, really are concerned with cost because it is a low margin market. And honestly, we're adding new attack vectors, remote attack vectors, as time goes on. A few years ago, Wi-Fi in a car wasn't something that was an option. Now, in America, you buy a new Ford F-150 and it almost comes standard with in-car Wi-Fi. We're adding features, but neglecting security. Everyone wants to slap crypto on everything, right? And that'll solve the problem. And I don't know if it will do it for automobiles. If your access to Gmail is a bit slower because you're using SSL instead of clear text, not really a big deal. At the same time, you wouldn't want a delayed airbag deployment. You wouldn't want a delayed response when braking. You wouldn't want a delayed response when letting go of the acceleration pedal. People, I guess, don't understand that auto manufacturers are really concerned with time. They have to have them work on the time frame that they want. They don't have any margin of error. The airbag deploys on time, or it doesn't, and you die. It's non-negotiable with them and as a client, someone who drives a car. The keys for these things are problems as well, because you can't really use PKI for this, and the keys are going to need to be shared. So they're going to be on the mechanics tool and on the ECU. We showed how easy it was to get it from a mechanics tool, but I'm certain we could have got it from the ECU as well. We just were better with, Windows stuff. Obscurity to protect drivers is just that. It's the guise that all this stuff is super difficult. There is a high barrier of entry, but After that, you can really start working on a lot of these. It took us 9 months to do our first line of research. If someone were to give me a car again and ask for similar research, I would be confident to say that I could do it in 2 months or less. So the more practice you get with these things, the easier it gets. A statement that struck us very oddly was by the CEO of the Alliance for Automobile Manufacturers. And it basically said that the reason car security is good right now is they've done a very good job of keeping the information out of the hands of the bad guys. If your security practice is, let's make it so bad guys can't just Google how to hack your car, it's probably not a good one to stand by. Charlie and I were basically nights and weekends with this. We had real jobs. I couldn't imagine if you had state sponsorship with unlimited funding and unlimited resources. You could really finish these things quite quickly. So, you know, obscuring information is just adding a small hurdle. Segmentation is good on its own. It's, you know, it would be some advice I would give, but it's not always the answer. You may be able to segment the very important things like steering, braking, and engine control, but then you're going to need to implement gateways as well. Have you ever been in a car where you start traveling quickly and the audio will turn up in volume, right? There's a reason that infotainment system's on the CAN bus listening for the speed. So they, you know, there's either a gateway or they just jack it right in. They don't like changing their whole designs. So segmentation can work, but then it adds complexities. And I know automobile manufacturers, when doing these things, hate adding complexities. We thought, coming from, I mean, I used to work at ISS writing intrusion detection, intrusion prevention systems, and, you know, being an offensive security person, thought about detecting attacks. Charlie and I always assume everything can be hacked. Assume you're owned, right? Assume someone will own you. I think it's naive to think that something is completely secure. Why is it advantageous to try to detect and prevent attacks? As I said before, vehicular networks are really well suited for this because the manufacturer knows what traffic it should be seeing, right? Because it adds these ECUs into the car. It knows how often these messages come out. It knows, you know, what kind of mechanics messages it can do. Attacks tend to stand out like a sore thumb. If you're seeing security access bleed brakes while the car is driving, it's very, very easy to see from regular general traffic, right? So Charlie and I did a test. We each took our car and drove it around for 15 minutes. And then we took the first piece of the capture for 1 second and then went through various places in the file, found that frequencies were almost identical everywhere in the file, and also no new CAN IDs were seen in that driving. And we did everything. We went, you know, pre-collision system, cruise control, everything like that. Cars really do have a baseline. The network traffic you see, the IDs that you see for driving are pretty standard. If you were to see a mechanics messages pop through there, it would stick out instantly from the rest of the traffic that you see. I talked about frequency before, right? And I said we took a sample of 1 second in these huge captures, and then I went every other place, you know, did a bunch of random samples of 1 second of traffic. And we found that the frequency of these IDs stayed pretty close. There was very little deviation from the mean, right? As I said before, how we got steering to work, we flooded the network with invalid speed messages. This, again, would stick out. If you're used to seeing 100 speed messages a millisecond and you're seeing 10,000, at the very least it's suspicious, and at the most it's malicious. These are easy to detect because cars are pretty standard. As a manufacturer, you know what you should see on your networks. And I said before, Diagnostic messages are for mechanics. I know there are probably some that are used while the car is in operation for things like OnStar or SOS. I understand that you can't block all diagnostic messages, but at the same time, you could have a very small whitelist of messages that are acceptable to be seen while the car is in function. The rest, such as security access, probably can, be done without. What can you do with all this happens? You can audibly alert the driver, beep, beep, beep. You could visibly alert the driver, little light that says, hack attack or something cool like that. You could shut down the CAN network for a brief period of time. Since it's 2 wires, you can short CAN high and CAN low, and that'll take down the CAN network. If worse comes to worse, you could just stop the vehicle. I think, with the steering, you saw how violently the wheel was turning. If that attack were about to happen, I'd much rather have the car stop than the wheel turn in that nature, right? You can ignore messages for a while. Steering actually is a good candidate for that because we were telling it to turn the wheel, which happens when the car is in auto park mode. So if it was seeing these messages and thought it was suspicious, it'd say, hey, ignore messages that are used in auto parking for right now. We're going down the highway. We're driving 80 miles an hour, things like that. Lastly, you could even start adding them to memory on the ECUs, on the EEPROMs, right? Cars will keep track of how many times the rev limiter has been hit. Why not keep track of how many times you've seen suspicious network activity? Then if there's any question involving an accident or something like that, they can pull memory off the EEPROM and say, hey, you know what? Back in January, there appeared to be a bunch of suspicious messages involving steering. So there are things that you can do. You can put these a lot of places. You can put them in every ECU, which is probably costly because you have to redesign the code for that. You can add an external kind of IPS to each CAN network. And we're even, Charlie and I are even working on a little ODB2 dongle that you can just plug in. You know how insurance companies do the tracking, see how you drive? Charlie and I are developing right now a little ODB2 dongle that's our IPS that'll alert the driver if one of their attacks happened. And we talked with the researchers from the University of Washington, and the University of California, San Diego, and they described their attacks to us and our detection mechanisms that I just talked about would detect those as well. So for all intents and purposes, all public car attacks that have been talked about would actually be caught by the methodologies I just talked about. Conclusions to this are, automotive attacks usually happen in 2 pieces, right? First, you remotely pop the car or stick something into it. Then you figure out what to control in the car via the CAN bus. Vehicles obviously can be physically controlled over the CAN bus, and I think as time goes on, more and more features will be implemented by the CAN bus. It's easier. It saves them money. That copper wire, the twisted pair, is all over the car already. If a company is saving a couple feet of copper wire per car and they're making millions of cars a year, I'm sure that adds up to a substantial amount of money. So that's why the easiest way is to just jack it right into the CAN bus. I'm not a big fan of relying solely on one security practice. If you tell me that we thoroughly test our external entry points and there's no way to attack them, I just tend not to believe you. My job relies upon being able to do the impossible every day, right? Someone will always say, here's a product, bet you can't break it. I get paid to break it. So there's people out there that are better than me for sure. So you can't just rely on one thing. I would personally like to be notified of attacks if they're happening, as opposed to blindly trusting my manufacturer to tell me everything's going to be okay. And layer it. There are good methods. You segregate. You do test remote entry points. You do have third-party evaluation of your code. You do, run some kind of detection system. And if you have this layered approach to security, I think that automobiles will generally be more secure. And I want more tech on cars. I think it's so neat. The concept of cars communicating with each other, vehicle to vehicle, is amazing. But we all need to sit down and think about the security of this before we blindly start implementing it all as well. So with that being said, I'm done. Thank you very much for having me here. Thank you, Code Blue. I really appreciate it. Arigato. I'll also be around here all day, so if you don't want to ask a question now, feel free to find me in the hall, or maybe we'll have a cup of coffee.